Okay, here in this part, what we're going to do is we're going to revise a bit on representation of systems of equation in matrix form. So here we know that, I'm going to take a red pen, okay. Let me test my red pen, okay. Okay, so now in representing systems of equations in matrix forms, we know that it can be written that the matrix of what we call matrix coefficient of A multiplied by a matrix of the unknown X, column matrix of the unknown X equal to the column matrix of the constant B, right? So A is a square matrix. So here we have an example over here, illustrated over here. A is what we call a coefficient matrix, a square matrix. So here's an example of 3 by 3 matrix, which means that it is a representation of a systems of equation with 3 equations. So in order for it to be solvable, you need for 3 equations, you need therefore 3 unknowns. So the unknowns are represented here in the column matrix of X, right? So here the unknowns are called X, Y, and Z, and equals to, at the end, you have column matrix of what we call the constant, right? So what does this represent in terms of systems of equation? So if you want to know what this represents in terms of algebraic equations, what you need to do is to develop the matrix, or develop the matrix again. So it's basically a systems of 3 equations with 3 unknown of X, Y, and Z, and the equations are, if we could write it again, so it's A1 X B plus B1 Y plus C1 Z equals to D1. So that's for the first equation. The first equation would be, as I said just now, it's A1 X plus B1 Y plus C1 Z equals to D1. And then the second equation will be so we go to the next second line, A2 X plus B2 Y plus C2 Z equals to D2, right? So it's A2 X, the first unknown, plus B2 Y plus C2 Z equals to D2. And finally, the third equation would be A3, so you know by now, A3X plus B3Y plus C3Z equals to D3. So here we have the three equations with the 3 unknown X, Y, and Z that are to be solved. So written in matrix form, it would look like such. Okay, right? So why is this useful? Why is this form of matrix is useful? Of course, later we will try to go, I'll try to explain more on it, as there are manipulations of matrix that are easy to be done in order to get to the solutions. But before that, I think it is necessary for us to do some examples or a bit of training on representing systems of equation into a matrix form. So now here what we've seen is from matrix forms, we go to algebraic equations forms. And now what we're going to do next is trying to go from algebraic equations into matrix forms, because what we want is for the equations to be written in matrix form. So, okay, so in this exercise, what we're going to practice is we're going to, according to this problem, following this problem, what we're going to do is from the systems of algebraic equation that we get from the problem, we will try to put them in form of matrix, right? So before we start, I'll explain a bit on the problem, on the background of the problem. It's a static problem where you have a truss of this triangular shape that is subjected to a force, to a load of 1,000 pounds, and the truss is connected or is kinematically linked to the ground by these 2 connections. So the first connection is a pivot, so there's going to be 2 constraint force H2 and V2, and on the second connection it's a slider where you have one constraint force called V3 in vertical direction, and the load is also in the vertical direction. So here we have in the truss we have three arms of what I'll call the arm 1, arm 2, and arm 3, right? So in this problem we will have a few unknowns that we could look for. So the first three one would be, of course, the force developed in those arms, which are F1, F2, and F3. And of course, there's also the force that is related to the constraint of the connection to the ground, which are H2, V2, and V3, right? So here what we have is we have 6 unknowns, right? Unknowns. That means that we would need 6 equations in our systems of equation in order for it to be solvable, right? So how do we get there to get the equations? So basically in this exercise, the objective of the exercise of the example is for us to practice transforming the equation in form of algebraic linear equation into matrix form. So we're not going into details, but basically what you need to do is you need to go through your static courses, basically. So what you need to do is to isolate each arms, and on each arms what you can do is you do your free body diagram, for example. And on each arm, for example, in arms number 1, when you do your free body diagram, there's going to be force that's affecting the arm vertically and horizontally, right? So vertically and horizontally, so there's going to be one line of equations of all the forces acting on the arm vertically, and then there's going to be another equation that's affecting the arm horizontally. For example, H2 going to affect the first arm horizontally, but this load of 1,000 pounds going to affect the arm 1 vertically. So 1 FBD, so this one arm will lead you to one free body diagram, right? And one free body diagram will lead you to vertical equation and horizontal equation. So there's going to be vertical equation and horizontal equation. So you know that for each truss, for each structure, each arm of the truss, you have 2 equations. So that we have 3 structure that will lead us to 3 equations. So here are the 2 times 3 equations. So the 2 equations of the 3 arms. So here we have the equations. Equation number 1, number 2, number 3, number 4, number 5, number 6. So now what we're going to do is to transform all these equations in matrix form. So a reminder again, in matrix form, it would look like this: matrix A of the what we call coefficients multiplied by the column matrix of X, right, which is the unknown, equals to column matrix of B, which is the constant. So now what is our X? The easiest way to start with is to start with our X. So the X are our unknowns: F1, F2, F3, H2, V2, V3. So they are all in here in this equation. So you can find F1 over here, right? You can find F2, F3, H2, V2, and V3. So let's write it. Let's write the column of the unknown first. All right. So let me see. So there's gonna be a column of coefficients. So coefficient is the multiplier of your unknowns, and then there's gonna be a column matrix for your unknowns. So the unknowns are, I think it's a bit small. I'm gonna make it bigger. So 1, 2, 3, 4, 5, 6. Equals 2. we have the constant. So let's say I'm going to start with, so there's going to be F1, F2, F3, what else we have? H2, V2, V3. H2, V2, and V3. So here are the unknown columns. And then here is going to be a 6 by 6 square matrix, which regroup all the coefficients or multiplier of the unknowns. So for example, let's start with the first equation. So there's going to be 6 lines and 6 rows. There's going to be 6 rows and 6 columns, right? The rows actually represent the equations, the number of equations, the order of the equations. For example, the first equation, I'm going to start with first equations first. So the first equation is minus f1 cos 30, cosinus 30. So it's minus f1, so we have f1 here, it's multiplied by minus and multiplied by cosinus 30, right? So, and then it's plus f3 cos 60. So plus f3, so f3, the second row is f2, so there's nothing multiplied by f2. f3, there is f3 in first equation, it's multiplied by cos 60, so it's cos 60. It's a bit too small. Let me erase. Wait, and I'll make it bigger. Up. Let me make a bigger column, a bigger matrix. A 6 by 6. Hopefully this will be enough. So it's, we said just now, it's minus f1 cosinus 30. There's no f2, so 0 on f2. There is f3. f3 is multiplied by cosinus 60. And then for other coefficients, other unknowns, there is no other unknown. So there's going to be 0 for for H2, 0 for V2, and 0 for V3. All right, and then we go to the next equation. It's minus f1 sinus 30. So there is f1, but now it's multiplied by minus sinus 30. Are there any f2? No, there's no f2. Right? There's again f3. It's multiplied by minus sinus 60. So minus sinus 60. And then there is no other unknowns, but on the other side you have constant of minus 1000. So here it's nothing multiplied by H2, nothing multiplied by V2, nothing multiplied by V3, and the equals to, here we have a constant of minus 1000. Okay, I forgot for the first one, there's no constant, so it's equal to 0. And then we can easily continue with, for example, here we can see that all the constants are 0, 0, 0, except for the second equation. So the rest are also 0, 0, 0, 0, 0 for the constant column matrix. And then we're going to continue with the third one. So there is H2. H2 is in, if we see here, H2 is in 1, 2, 3, 4, in the fourth row. So, but there is F1. So F1 is, the multiplier is cosinus 30. And then F2, there is F2, just multiplied by 1. There is no F3, but there is H2 multiplied by 1. And then that's about it. 1, 2, 3, only 3 unknowns. 1, 2, 3, and the rest are 0. Okay, so for the fourth line, we have V2 and F1. So F1, the multiplier is sinus 30. And then we only have V2, which is over here, the fifth line. V2, the fifth line, the multiplier is 1. So the rest are 0. Fifth line, there is minus cosinus 60 F3 and minus F2. So F3 and F2. So F1, there's nothing. F2, there is minus 1. F3, there is minus cosinus 60. And the rest are 0. And at the end, by now, I think you know how to do it. There's F3 and V3. So F3 is over here. The multiplier is sinus 60. And V3 is the end of the line. And the multiplier is 1. And the rest are just 0. So there you go. There you go. We got the matrix of the coefficients. So now we have the systems of equation written in matrix forms. Right. So now let's continue with practicing putting our systems of equations into matrix form with the second example. So in this example, it's a bit more interesting. So what we have here is it's a problem of dynamics. We have imagine that we have three acrobatic parachutists that jumps off an airplane and fall freely to the ground, but they are all attached by a rope that attached in between the parachutists. So they fall vertically, like illustrated in the picture. So I will call the bottom parachutist as parachutist 1, and then on top of him is parachutist number 2, and on top of parachutist 2 is parachutist number 3. And in between the parachutists, they are actually connected by ropes, right? So imagine that they are falling now at a given time t. They are falling at a speed of 5 meters per second. Okay, so now they are falling at a speed of 5 meters per second, and each of them have a mass as written here in the table below. So the mass and the drag coefficient of each person are over here. So now as they fall, what happens is as the velocity increases, the drag force also increases, because the drag force is proportional to the speed, right? And then the thing that we would like to know is the tension of the ropes that connect them. So the first tension is called the tension R. Second rope's tension is called tension T. And then we also like to know the acceleration on which they fall. So now they're falling at 5 meters per second, but what is the acceleration? Of course, these all three unknown parameters R, T, and A are the results of the gravity, G, the mass of the parachutists, and their drag coefficients, right? So if this change, then the tension and the acceleration would change as well. So that means that these three parameters R, T, and A are the unknown. So let's say now if we write the unknowns here, unknowns are the tension R, the tension T, and the tension A. So in order to find the three unknowns, you know that we need a system of three equations. So where do we get the equations? So briefly, this is not an exercise of dynamics, but again, so you isolate the body and you do a free body diagram of each body, and on each body you have forces that's subjected to the body. For example, in body number 3, the body which is on the top of the acrobatic configuration, you have, of course, the drag force, which is equal to the speed multiplied by the drag coefficient. So now the speed is, we are at 5 meters per second. The drag coefficient is written over here for parachutist number 3, 17. So this is known. The other two forces acting on body number 3 is the weight, which is equal to mass, its mass multiplied by the gravity. So this is also known. But now the unknown we have here is the tension of the rope between the parachutist number 3 and parachutist number 2. So R, we find it again over here, R, on free body diagram of body number 2. So the same thing, so now you have the force of the force that's related to the drag coefficient, the mass, and here you have another tension T, which connect the body number 2 with body number 1. So we find again here T, and so on and so on. So from the three free body diagram and writing your dynamic equations, it leads you to systems of 3 equations. So these are the 3 equations. First equations from free body diagram number 1, second from the second free body diagram, and equation from the third free body diagram. So now our objective is to write it in form of A multiplied by X equals to, equals to B. Okay, so as we did just now, the easiest way is to start with column B. So draw a big coefficient matrix over here, multiplied by the unknown equals to the constant, right? So the unknowns are, what are the unknowns just now that we said? So the unknowns are, there are 3 unknowns. There are R, T, and A. So here are the unknowns. So you could put R, T, and A, and then we can go through one by one the equations. So the first equation is M1G minus T minus C1V equals to M1A, right? So the only, so what are the unknowns that we have here? The unknowns that we have here is T and A. So you have to rearrange the equations in order to put all the unknowns on one side and all the constant on the other side. M1G is a constant. Why? Because M1 we have the value here. Mass 1 equals to 70 kilograms. G is equals to 9.81 meters second square, right? So this is constant. M1 is constant. C1V is also a constant because C1 is given in the table below. The value of C1. I lost my mouse. So C1 is over here, 10 kilograms per second. And V, we know that we had just now V equals to 5 meters per second. So these are also constant. So let's say constant. I'm gonna make the constant larger now. So now we have constant M1 multiplied by A minus M1 multiplied by G, right? And then as for the coefficients, there's nothing multiplied by R, so it's 0. Are there anything multiplied by T? Yes, it's minus 1. That is T. And then are there anything multiplied by A? Yes. I had it wrong here. Let me erase. So the constants are basically minus M1G and plus C1V. So it's C1V minus M1G. And M1A is not a constant because A is the parameter that we want to know. It's unknown. So it's A is over here. When you bring M1A to the other side, it's become minus M1A. So it's minus M1A. Then we go to the second row. Where are the unknowns? The unknowns are here, T and A. So again, the constants are M2G and minus C2V. Bring to the other side, it becomes C2V minus M2G. So as for the coefficient of the unknowns, there's 1 multiplied by T, and then minus, when you bring it over here, it becomes minus M2 multiplied by A. So there's nothing for R. There's plus 1 multiplied by T and minus M2 multiplied by A. And for the final equations, final line, the unknowns are R and A. So these two are the constants. Bring it to the other side, it becomes C3V minus M3G. So, and the unknowns, the coefficients of unknowns are 1 multiplied by R. So 1 multiplied by R. And A, bring it to the other side, it becomes minus 3 multiplied by A, minus M3. So minus M3 over here multiplied by A. And there's nothing for T. So there you go, the systems of equations that represents the problem of the three parachutists attached together in order for us to find the solution of the tension R and T as well as the acceleration A. That's it.